the session.
Okay.
I'm very happy to present our next keynote speaker, Professor Kristin Yvonne Rozier, who is the head of the Laboratory for Temporal Logic in Aerospace Engineering at Iowa State University. Previously, she spent 14 years as a research scientist at NASA, and she earned her PhD from Rice University. Her research focuses on automated techniques for the formal specification, validation, and verification of safety-critical systems from early design time to runtime. Her advances in computation for the aerospace domain earned her many awards, including the NSF Carrier Award, the NASA Early Career Faculty Award, American Helicopter Society's Howard Hughes Award, Women in Aerospace Inaugural Initiative Inspiration Impact Award, 2 NASA Group Achievement Awards, 2 NASA Superior Accomplishment Awards, Lockheed Martin Space Operations Lightning Award, as well as AIA's Intelligent Systems Distinguished Service Award. I was really happy to read through this list because we have a very distinguished speaker today. So please welcome Kristin, and the floor is yours.
Thank you so much. And for anyone who just arrived, I believe we announced that there is a way to ask questions during the talk as well as after. So if you put a question in the chat, then that will be read out loud during the talk. And then I've also left time for questions after. As you can see, the title of this talk is Developing an Open Source State-of-the-Art Symbolic Model Checking Framework for the Model Checking Research Community. And those last words, for the model checking research community, we really wanted to emphasize those on behalf of the project. And so create lots of opportunities for discussion and interaction and leave you with ways to become involved in this project. So first, I will start off with a diagram that probably everyone here is quite familiar with, the automata theoretic approach to model checking, right? So I've cited the seminal 1986 paper by Vardy-Volper, where we have the ideal of the idea of model checking has formed, right? We have our formula phi, we negate it, we encode it. In this case, it was explicitly right in the form of an automaton appropriate to the logic that we use for phi. And we, of course, have also an automaton representing our system model M. Then I have bolded in the middle, right, this Cartesian product. And this is where the magic happens, right, where we take a neg phi, right, the automaton representing the negation of our desired system requirements, and our M, and we combine these and see if the resulting set is empty, right? So first we have the idea of using automata to do this, and then of course this leads to an explosion of all sorts of innovations, right? And in terms of how do you do this arrow, right? How do you encode phi as an automaton? There's many ways to do this. For linear temporal logic, for example, to a Bushi automaton, there are several different ways to translate this. Which one's better, right? Do we have smaller? Do we have more non-deterministic? Do we have larger and more deterministic? And then, of course, ways to do this Cartesian product, right? Do you do it all at once? Do you come up with sort of on-the-fly techniques? What are the best ways to accomplish this? So we have this initial seed that leads to an explosion in different directions throughout this diagram in terms of model checking research. And one of the directions that also came from that diagram, this is the same diagram actually, except using a symbolic automaton representation instead of the explicit automaton representation here. So yet another direction, and this is in 1997 by Clark, Gruberg, and Hamaguchi, is what if we represent all of these instead of explicit single state, single transition automata, if we use symbolic representations where we represent sets of states and sets of transitions, right? And then how does that change this arrow here? Because of course, now we have to take some LTL formula like P until Q, and we have to represent this symbolically. And this is, by the way, the real and complete symbolic representation from this paper from 1997 in the SMV language, which at that time was used for Cadence SMV and New SMV. And of course, today, this exact same thing works with the current version of those New XMV. And essentially, the algorithm was to declare a module representing the automaton. Of course, we declare the system variables, and then this paper has a scheme for creating sets of elementary variables. In this case, we need just the one representing a postponement of the promised P until Q property. And then there are the transitions you would expect based on a definition that makes it easier to read. So we declare a definition for the whole property here of the property P until Q is, of course, either Q is true now or P is true now, right? And we have our postponement variable. And then we have the appropriate transition, right? That this next time here in the name of our elementary variable really represents a next point in time. This incorporated fairness. So we had that we needed this fairness property, right? Of either our formula is not satisfied or we have the eventual promised Q. And then, of course, we had a translation here that incorporated a spec that merged several different formats. In this case, this had a CTL operator, but there was an LTL formula here. So we are building on top of a model checking framework that was initially optimized for CTL. And in this case, in our intermediate representation of LTL, right, we're utilizing the CTL optimizations that have been built into the model checking frameworks at this time. And that's an interesting thing to note, right, because we want to evolve that over time. But at that time, CTL model checking had been looked at first. And so we use that in our encodings. And of course, this is a fully working model. It's the universal model because it fit on a slide. And so you can just specify no states or transitions, which means they're all allowed because SMV chooses non-deterministically whenever you don't say something. And then, of course, right, we still have this interesting research area here of the Cartesian product going on and how to do this non-emptiness check, right? And like I said, this still works today. But we've also had a lot more exciting developments that have even built on top of this. So I want to say in the rest of this talk, as I unroll these, I mentioned specifically in this slide, right, that we were reducing to an underlying model checker that had CTL implementation. But ever since the 2001 final showdown, which is literally the name of this paper, we consider CTL to have passed in its time. And so from this point in the time and the talk forward, I am talking about linear-based logics that reason over linear time. And specifically, I will use LTL as an example, but of course, people have created many variations on this that I'm also including. So from here on out, let's look at LTL. And also from here on out, I'm going to concentrate on examples from what we call hardware model checking, right? So I gave an example of SMV in the first couple slides. This was a model checker meant to verify protocols, hardware logic, this sort of thing, algorithms, as opposed to software model checking, where we're looking directly at verification over C code and Java code. It's very important to note that I am not excluding software model checking. So I hope that the developments that we are proposing, especially at the end of this talk, they definitely have traceable impact on Symbolic, on software model checking, but we are concentrating for the series of examples here on hardware model checking. And so I'm not going to be speaking specifically about aspects of programming languages such as C or Java that are popular in software model checking. We're going to focus on just representing hardware model checking very well, and then looking at expansions and implications from there for related verification techniques. Okay, so looking now at LTL, at hardware model checking, and continuing on our progression, right? We now have this explosion of symbolic model checking becoming very, very good. And so now we've moved ahead to 2007, and this is a paper that I wrote and a graph that I made. And you can see here are it's every encoding of linear temporal logic for explicit state model checking that was available at that time when I ran this study. And then you can see here are new SMV and cadence SMV, two versions of a similar symbolic model checker at the time. And you can see the performance is not even close, right? So in this case, I am exemplifying their performance in the example of satisfiability checking. So using a universal model, like I showed you a couple of slides ago, to check satisfiability of the temporal logic formula, but we get similar results if we fill in a more restricted model. And you can see here, right, we have a median total runtime, and then we have a scaling of the size of the formula, and explicit state model checking at that time was limited to this region of the graph, whereas we were exploring wholly new territory as soon as we moved to the symbolic representations of the formulas and of the models. So we keep having these exciting push forwards, and this is about the time where software model checkers really push performance to industrial levels. So we're starting to see a lot of adaptation in the aerospace industry, for example. We're starting to see people using formal verification for flight systems, for railways. It's really come to be something that we can rely on in industrial settings and not an academic tool, right? And highlighting that, particularly the aerospace settings, we're able to then build fancy things on top of symbolic model checkers that allow us to specialize them to verify these industrial systems even better, right? Here is an example of the real automated airspace concept from NASA Ames Research Center. We had a verification project over this system where we looked at defining in the SMV input language via a collaboration with the creators at FBK, of course. We modeled conflict areas. So you can see here that we would have multiple aircraft in the airspace, and we could reason about their trajectories and when they would have conflicts with each other in terms of losing what NASA had defined to be safe separation between the aircraft. Another really exciting thing we were able to build on top of new XMV in this instance was time windows. So we also evolved how the aircraft were related to the rest of the model, where they were situated in space over time, and in very interesting and impactful ways that mirrored quite precisely exactly how the automated airspace concept was modeling these. So in the AAC, there were notions of the current location of an aircraft, and then its near-term, mid-term, and far-term plans or trajectories of where it was going to go. And then the safety properties also reasoned over these, right? So if you are here, if it is so long or so far until you reach a certain place of interest where there might be a loss of separation or a weather event or something else that you need to accommodate, right? A communication zone where you might have to communicate differently. or rely on a different system for separation assurance, right? How do these things relate? So we were able to represent things in a symbolic model checker that had not been represented before, because by this point, the model checker could handle it, right? And we put in all kinds of different options. So now instead of that one diagram that I showed as the very first slide, where we have one property and one model, right? Now we have a design space. We have a lot of different options. So we actually have a large set of possible models, right, in this design. And they vary in terms of different parameters, like do the aircraft have, for example, ADS-B out only as their communication protocol? Do they also have ADS-B in as a communication protocol? What does that mean in terms of the information and how we can prove things about information getting to the right place at the right time? We were able to do things like mix GSEP or ground separated aircraft, so aircraft separated by an air traffic controller on the ground, with aircraft that were self-separating, so aircraft running separation assurance algorithms entirely on board and not taking directions from the automated air traffic controller. And we were also able to model all kinds of interesting combinations of these, right? So maybe there are places or times where an aircraft might be ground separated and places or times where that same aircraft might be self-separating, and it switches between the two. So we're able to represent lots of complexity, lots of options. And that ended up, we've summarized it in this table, which appears in this paper if you want the details. But the really important parts I've highlighted here in this corner, in that we ended up with over 20,000 realistic options for this design space of the AAC that we are able to verify using a symbolic model checker. In fact, we now can verify so many realistic designs using a symbolic model checker that it's actually more than the humans designing the AAC want to weed through. So we actually had to narrow down the results to a human parsable number of 1620. So out of these, right, we were able to come up with parameters. What makes this one less safe? What makes this one less desirable? Obviously, some of these had counter examples, right? So they showed that if you design the airspace in this way, the model checker can tell you, no, this requirement is going to be violated. And here's a counter example, right? So we can clearly eliminate all of those. We can eliminate some of the ones that work, but maybe work in less desirable ways, maybe that are less usable, things like this. And so we were able to narrow in on 1620 models to really analyze in depth, add more to, and present to the customer at NASA. And when I say things like add more to, I mean things like this, right? Because now we can also do things like build fault tree analysis on top of a symbolic model checker. So we can take models, we can take requirements, we can tell our system designers what happens if everything always goes right all of the time. Here's which systems are not provably always safe, right? And here's what can happen with them. And now, what if we have faults? What if we have things that you expect to happen periodically, right? Then which ones of your remaining set of designs have single points of failure? Which ones have, certain are more susceptible to this kind of failure versus that kind of failure, that sort of thing. So we were able to expand on this in many ways. So symbolic model checking has really become a powerful and impactful tool that actually did change the design, the real design of the automated air traffic system, the concept at NASA. So we also have at this time, though, in addition to building all of these things, right, what's under the hood has been rapidly evolving. That's part of the story that I want to make sure that we really consider here. So back when I showed you those first graphs, right, when I showed you that first conception of symbolic LTL model checking, the symbolic reasoning, that Cartesian product and the representation under the hood, that was entirely BDD based, right? So it was based on Ken McMillan's first stab at symbolic model checking for CTL, which carried over into LTL. And then we evolved more things, right? We got SAT based, we got bounded model checking. We discovered this amazingly efficient way of finding bugs with bounded model checking, right? We also then, after 2012, we got IC3, right? And eventually we added on K-liveness to make that complete. So we have been moving the progression of the algorithms under the hood, and that's a lot of what's driving all of these advancements in what we can do with symbolic model checking, right? And really notice on this list that we also see a progression from bit level to word level. So our intermediate representations that we are using, for these algorithms has really evolved quite significantly since the conception of model checking. So now we come to the current state, which hopefully is not covered up by my Zoom window up here for you guys, but that was history. And then we come to the current issues that I want to address in symbolic model checking. And this is an example of one of them. So this is another paper where I was looking at using symbolic model checkers for satisfiability checking and model checking of linear temporal logic formulas. And you can see from the first graph, right, where we had the explicit state model checkers for similar problems. And then we had cadence SMV and new SMV were just in a different universe in terms of performance. Cadence SMV was the best line on that graph, right? So this line that you can barely see because it is so close to the y-axis, that is the same line of cadence SMV from that very first graph I showed you. And this line here, so this is log scale, this is exponentially faster. This is a line created by encoding the LTL formula, the intermediate representation of the LTL formula, using a new algorithm called Panda. And so here's the comparison in performance between reasoning over the previous representation of the same formula for a large set of formulas and the new representation of this formula at an intermediate level. So you can see we can get exponential improvement in the performance of the model checker by the way that we represent things. But we have an issue here, right? Because I wanted to incorporate this into model checkers like cadence SMV, right? Imagine if we could put this in the model checker, if we could then build on it further, but this was closed source. So I could compare this, and cadence SMV had a very particular way that one could use a command line flag to feed in an intermediate representation of a formula, but not necessarily of the model. And that's what I used to do this study. But the study was essentially stopped there, right? I couldn't progress forward in terms of integrating this. It was really hard to compare this in other ways. And we see that this problem just continues getting worse. So here is a later study. It's getting more recent now. This is from 2017. This is where one of my PhD students created a new IC3 backend called Fuse IC3, and it is specifically tuned to be able to very efficiently perform model checking over large design spaces. So you'll recognize the number 1620 down here. Those are the same 1620 models from that NASA automated airspace concept that I showed you some examples from earlier. And in this case, we have a graph here where we are comparing 3 different algorithms. So the best IC3 algorithm at that time is represented in these blue X's. So you can see its performance up here. And then there was a incremental IC3 algorithm that was also meant to reason over sets in the same way that Fuse IC3 is. that came out from IBM. And so you see that represented here. And then you see the Fuse IC3 algorithm, which is represented here. Now, this is a really cool advancement in model checking. But what is not really cool about this is that in order to get this graph, in order to be able to compare these algorithms and know whether what we had created, whether Fuse IC3 was actually worthwhile, worth pursuing or not, Rohit actually had to completely implement a model checker from the ground up. He had to completely re-implement these algorithms, start to finish, as well as Fuse IC3 in order to compare apples to apples, right? In order to have a fair and just comparison where all of these are implemented in the same model checking engine, in the same programming language. We're not getting some difference because someone used a different compiler or someone's a slightly better programmer than someone else or something that has nothing to do with the actual algorithmic comparison that we're trying to make, right? There was absolutely no way to do this comparison other than by writing an entire model checker from scratch, right? And then what's the point of that model checker? Exclusively to make this graph, right? So this serves as an impediment to the progression of model checking research, exactly the things here, the algorithms under the hood, the advancements that we're seeing that caused symbolic model checking to explode into this place in industry where it's usable. That is limiting our forward progress from now, right? So it's doing exactly the opposite. This is really an issue. And we have some attempts to standardize hardware model checking, right? So I find it's very important to highlight that at the same time, we do have the hardware model checking competition, HWMCC, and this has progressed over time from bit level to word level reasoning, just as symbolic model checking has. And the latest version of this competition, for example, it's used various different formats throughout the years since it was started in 2007. But in the latest rendition, it is using BTOR2 as an output language. So we have a little bit of standardization going on here in terms of what do the outputs look like. And that allows us to do some comparisons. So for a limited amount of comparison that we can do, right, we can run some benchmarks and we can compare the BTOR2 outputs of model checkers. And then we get this. And you see that despite the difficulties, we still have some phenomenal research going on in model checking, right? We have this AVR model checker that has done phenomenally. We have PONO, we have ABC, we have all of these other model checkers breaking into the scene that are doing phenomenally well. And we need more ways to compare them than just this, right? So we have a very limited expression language. We have a very limited experiment here. There is a desire that you can see from all of these people competing in the HWMCC to come together in one place, to be able to unify, to be able to compare, to say which model checker is best for this. But we don't have a good way of doing that on a deep level. We don't have a good way of advancing research. So this problem has been continuing to get worse over time, right? So like I highlighted, some model checkers that are phenomenal are closed source, right? So new SMV used to be open source, but of course its latest version that has the most advanced IC3 algorithms in it, new XMV is closed source. So we have some instance of that. We have some other phenomenal tools like ABC, like all of the other tools, AVR, things that I mentioned at the hardware model checking competition that are open source. So that's wonderful, but they are quite limited in terms of the advancements in modeling, the phenomenal things we were able to do with the AAC that I highlighted in previous slides. Those are not available in the current open source tools, right? So we have these capabilities that we know that we can do. We have phenomenal things that have been built on top of model checkers. I happen to be highlighting, picking on, depending on your point of view, new XMV, but it's definitely not the only model checker that has had this sort of evolution, right? And so we have expressive languages, we have tools built on top of model checking, we have other model checkers that are open source that maybe we could build on, but they don't have the same capabilities. They have useful languages, but one language is not useful for everything, right? That's why we have lots of different modeling languages for model checkers. And we don't really have a unified open source research enabling connection between all of the rich set of modeling languages that we have used for real world verification and the complete set of state-of-the-art backend model checking algorithms, right? As we've had these advances in backend model checking algorithms, they have each been published very reasonably as here is this algorithm implemented in this one model checker, right? So now if you have this algorithm in this one model checker and this algorithm in this one model checker, and you are creating a third algorithm, now you have 3 different model checkers that you have to somehow unify in order to be able to try out whatever verification technique you're going to use. So the way forward, we have proposed and won funding from the National Science Foundation in the United States to create a standard for the model checking research community. The grant from NSF has the same title as this talk. And here is one of our summary graphics, where the idea is to have a unified standard that incorporates an intermediate language in the center of model checking. And the idea is that we want to create something here where any sort of representation, front end, right, your temporal logic formulas, you could have Eiger format, which is a format that has historically been used in the hardware model checking competition that is for and order graphs. It's quite limited, but it served its purpose as a standard. You can have different things like those rich SMV models, other sorts of representations of time. You can have all sorts of logics and modeling languages that provide rich expression, that provide specification to different real world verification problems. And each of those could be added to the community model checking standard simply by making a connection to this intermediate language under the hood, right? And then similarly for all of the backend algorithms here, right? So we could have still the best BDD-based algorithms, SAT-based algorithms, IC3, PDR, K-liveness, any advances in these for single model formula verification, for design space verification, right? As members of the research community contribute better algorithms, all you have to do to contribute a better algorithm is to create a translator to and from your backend reasoning engine and the intermediate language. And then that would suddenly enable you to, for example, check any models that were developed in any of the modeling languages. And you would be able to compare to the performance of other backend algorithms simply by creating a translator and hooking in your new modeling language, your new algorithm to this standard, right? So this provides a much easier way to advance model checking research. And in particular, when designing the intermediate language, we wanted to take into account this specific set of goals that I have on the slide here. So we wanted to allow adding a modeling language to the community standard by the one single step of translation to and from that language. Then you can use any backend. So for example, if I have these NASA AAC models that represent very precisely, that are specialized to what we needed for this industrial aerospace application, I can now use any backend, even if it was from a model checker like ABC might have the most fantastic backend, but it doesn't currently accept models in this format, right? No problem with this new intermediate language. I can now have my rich modeling format. I can use a backend that was developed by anyone in the research community, and all I have to do is create a translator to be able to do that. So it enables verification, enables comparison, and it enables a faster progression of model checking research into the future, because we don't have to do things like re-implement the entire algorithm from the paper that ABC published about their phenomenal new backend. We can just use it, right? Similarly, adding a new backend algorithm. If we want to know whether our new variation on IC3 is better, worse, sometimes better, how it compares, etc., to every other implementation of IC3, all we have to do is create a translation to and from the intermediate language, and then suddenly we can compare with not our implementation of other people's algorithms that maybe we implemented it not as well as they did, right? People know their own algorithms very well. They are invested in optimizing them, right? We can compare against the original implementation by the authors of the algorithm simply by creating a translator. And then we're comparing apples to apples, we're reasoning over the same models. We want to make sure that this language, though, is efficient and accessible, because, of course, we also showed that the intermediate representations and how we reason over them can have a tremendous effect on the performance of model checking. So the idea is to continue that forward trend of model checking becoming ever more scalable and ever more useful, right? It's very important to design something that enables that to continue. We don't want to get bogged down with an overly expressive intermediate language that becomes horribly inefficient. And the idea is to really get community buy-in so that we can create something that will be an ongoing standard for the research community, so that we can have even more research, an explosion in research as to how to do the translations to and from modeling languages, to and from backends, so that we can really maximize the performance in the future. Similarly to how in the past we said, okay, we're going to represent LTL as an automaton. And now we can optimize the translation of LTL to automata and figure out which is the fastest way and why and when. We want to have a similar thing happening with an intermediate language here. So we had a basis that we have worked off of for our initial draft of the intermediate language, which I will highlight bits of in the next few slides. But you will recognize a lot from SMT-lib. So our language is not SMT-lib, and it is not backwards compatible with SMT-lib. However, the general sentiment of SMT-lib has highly influenced the design. So you will see some SMT-lib-like constructions in the intermediate language draft that we have. We also looked widely at several different intermediate languages, both how they were designed and how they were used. So we had presentations from the authors of languages like VMT-lib Iowa, the confusingly also named VMT-lib that was created by FBK, the intermediate language Sally from SRI, Cryptol, which is from Galois, Okra, which you saw actually highlighted in the AAC verification work for the scalable model checking. We looked at things like synchronous reactive components. We looked at a wide variety of related work of what is currently used from that, what are the highlights, and what has maybe become a product of history and we are able to build forward, right? So we looked at the best of all of these to combine them. We integrated in feedback from the authors of all of these at our group meetings so that we could really have a deep understanding, both from literature and from being able to ask them questions as to what's working, what might you change if you could. Of course, we want to have our intermediate language be relatively simple, but it needs to be complete, right? We have to be able to have sufficient expressibility to represent the models that we intend to model check and be able to handle representing the inputs and outputs to the backend reasoning algorithms. We're looking for this to be easy to parse, of course, and by a machine. So it's an intermediate language. It's not maybe the most human readable thing, but that's okay, because the idea is that humans would use a high-level modeling language to interact with the model checker, right? That's part of the whole point of this. So we want to make something that is sufficiently easy to write an automated parser for, that we can really optimize, that we can create very, very fast translations into and out of, but it will largely be read only by humans when they are developing these tools. And of course, we wanted to really look at what are the translations that we want to have implemented, what do those look like, really have experience with this language. So the draft has been evolving as we look at translating into and out of it. So when I say we, these are the people that I'm referring to. We have a core design team that has been meeting about this every week. So I mentioned an NSF CCRI grant, which stands for SIZE Community Research Infrastructure. SIZE is the computing department of the NSF. So I'm the principal investigator on the grant. We have co-investigators of Natarajan Shankar at SRI, Cesare Tonelli, who is also, of course, deeply involved in SMT-Lib, and he is at University of Iowa, and Moshe Vardi from Rice University. We also, very importantly, of course, have PhD students, and of course, they're the ones that are actually doing the implementations of this. So they are doing a ton of work in this area and have also contributed fantastic insights. We have Laura Gamboa Guzman from Iowa State, Chris Johansson also from Iowa State, and Yilin from Rice University. And then we have had a couple of meetings with our technical advisory board, and then updated them also by email and sending drafts of the intermediate language, taking in their feedback. So we have a fantastic group of people that have been involved in multi-hour long meetings, that have come by and given presentations on their model checking tools with our core team, answered our questions, helped influence our design in many ways. So I wanted to make sure to highlight the contributions of all of these people here. They have each signed in, given us feedback, written to us. So that's been very important. We have Rajiv Valor, Clark Barrett, Armin Beer, Nikolai Bjorner, Dimitri Giannakopoulou. We have Alberto Grigio, Orna Grunberg, Arti Gupta, Ari Gerfinkel. We have Ahmed Erfram at SRI, who has also been calling into our meetings recently. John Matthews, Kevin McMillan, Alan Mishenko, Karim Sakala, Bernard Stefan, Aaron Tolman, Stefano Tanetta. So thanks so much to all of them. And then in addition to all the people that I've put on these slides, we have had open community forums for anyone in the model checking research community to be able to watch a presentation, talk to the members of the core team, talk to members of the technical advisory board, and contribute their questions, comments, refinements to the language, etc. This is all still going on. And I wanted to highlight that how you can influence the design is right here. So I have a few different URLs for you. We have a homepage that is reasonably easy to remember. It's modelchecker.temporallogic.org. So everything is now and will continue to be linked from that page. But some highlights that are linked from that page is that we also have a GitHub organization. And currently, this mostly contains the results of the meetings and language development that our team has looked into so far. That's modelchecker.github.io. But the point of having a GitHub organization is that that makes it also very easy to integrate into the community and allow people to also interact with a public Git repository to contribute their own translations, to contribute their own research for the model checking community to build on. And I wanted to particularly highlight in the GitHub organization, we have a much more complete description of the current draft of our intermediate language than what I'm going to highlight in the next few slides. So if you're interested in reading about what we have so far and seeing all of our notes, they are all in the GitHub repo, and we welcome your feedback. So I will just highlight a couple of examples here of what our language is shaping up to look like. And then, like I said, we welcome your feedback as we continue to refine this and write the initial translators. So we have a SMTlib-like transition system definition. The bottom of this slide has a lot of text and is mostly just for your reference, but essentially, we're going to have a transition system that is named S here. And the idea is that it has an initial state, and that is going to have input variables, we have output variables, and we have local variables. And of course, all of these are optional, so you might fill them in or you might have nothing there. And then we're going to have the transition condition represented in terms of, we have the tick meaning the next time, right? So we have the sets of input, output, and local variables repeated again here in one time and then in the next time after that, right? So a reasonably simple definition. It is reasonably easy to parse and to write translators to represent transition systems into, and that has served as a basis for a lot of the constructions that we are defining in this language. I'll highlight this time without a lot of the definitions below, but the point is to see the format here. I'll highlight the system checking command that we have at the moment. So we're going to have a check system command over a system S that obeys the definition I showed you on the previous slide. And that will have the following optional set of components that you might choose to include when model checking the system. So we're going to have tuples of input variables, output variables, and local variables. So those mirror the construction of S. And then we have places to designate things like assumption, and we have different checks that you might do separately or in combination, such as checking for fairness, checking if some state is reachable. We have current conditions, and we have ways of specifying a single query or multiple queries. And one of the reasons that we have looked at things like this is because in interactions with our technical advisory board, we had questions about, well, what if you want to interact with a model checking backend that has options to check one property against the model and separately check another property against the model, right? And then you might have two different worlds where these are both evaluated, or you might have multiple properties at the same time, right, which represents a set of properties you're checking against your model, and you might want to return results that reason over the set. So it's important to try to create a straightforward way to represent those. And then we were looking at things like, how would people check for deadlock? And so you would have things like asking if a deadlocked state is reachable. So we have refined this several times. I'm not claiming that this is the definite final state of this. It might certainly, it's possible for it to be refined several more times as we look at translators, but this is the kind of thing we're thinking. So I hope to give you an idea of what that looks like. And then for my final example here, we would also want to be able to get the response back from the model checking backend. And so we are looking at different ways to be able to incorporate the check system response in their intermediate language. So we would have things like, you see the queries set up here. And a very interesting thing that we actually debated just a couple of weeks ago, and I think we're happy with how this is looking, but again, it's still in flux. This is literally up to the minute what we're looking at for the language, is looking at having a trace returned. For example, if you have a counter example from a backend, and a trace would have two parts to it. So it would have a prefix part and a lasso part, and each of the prefix and the lasso would be of type trail. So a trail is a finite sequence of states, And then when you're returning a counterexample, for example, to a safety property where you don't need a lasso at the end, then you would just have one trail that you could return from the model checking backend. And that could optimize because you are skipping having to represent an infinite trace when really you only have a finite trace. But then also we would have the capability, if you're checking a liveness property, right, you need the infinite trace with the lasso. So in this case, you could have this pair of trails in the form of a prefix lasso trace, where you would have the prefix and then the lasso, the last state of the lasso as a transition to the first state. So it's a succinct way of representing that. And we have, of course, ways to represent your model. And then we've been looking a lot at the bottom part here of how to also represent certificates, because a wonderful advancement in symbolic model checking that is just exploding right now is how to return certificates as opposed to a just yes, model checking succeeded results, right? How do we create a proof certificate that we can pass up that increases confidence, particularly among customers when we are verifying real systems, that the model checking result is correct, right? So looking at what is a really efficient way to represent the types of certificates that people are starting to incorporate into the latest symbolic model checking backends, and how we can handle that really efficiently in an intermediate language. So I wanted to show you, to assure you also that we're not just defining this and setting it off into wild. I wanted to show you our process here that has been actively under implementation, mostly by the PhD students that I highlighted in the previous slide. So we are looking at creating the initial translators from the SMV language, or a variation of it that we are calling SMV++. So it would have the core SMV language that has been used in many industrial studies that we want to preserve models that are represented in that language. And then also some of those features, such as the ones I highlighted earlier in this talk and others that have been developed since then, that have been added on to represent specific systems that have been proven to be very useful. So at the moment, we're hooking though to new XMV to create the SMV models that we would have at the front end. And we are also looking to tie into BTOR2 because, as I highlighted, that is the output language from the hardware model checking competition. So we are hooking into the tool BooLector in order to interface with that on this end. And then you'll see here this label PVS. So all of this is actually being defined in the PVS proof assistant. So what we are doing is we are creating theorems that our representation in the intermediate language is equivalent to the SMV model, and then a theorem that our representation in BTOR2, of course, carries the same equivalence. And so you can see the lines go down this way, right, where we have a model. And then we would need to translate that to the intermediate language in a way that's provably correct, down through it to BTOR2. And of course, we have the model checking going on back here, and then any witness, any counter example, or certificate that we might get from a backend model checker that we could fill in here, right? We need to be able to represent that equivalently in the intermediate language. And then again, represent that equivalently in the language of the original model, right? So a counterexample needs to have the same variable names as the model that generated that counterexample. And so we're looking here in PVS in this box at saying that these representations up and down the translations here are equivalent. And so the idea for generating the first translators into and out of the intermediate language that we will release into the model checking research community to build on is that we write these theorems in PVS, And then essentially the proof of the theorem, the proof of equivalence, is a translation between the two things we are proving equivalent. So then we have a wonderful tool called PVS2C that can take the proofs of equivalence that we have created in PVS and create a fully verified translator between our different representations as represented in this figure. So the idea is that this would serve as a core, as a basis that the model checking community knows is correct because it was generated from an automated theorem prover that people could build on. Of course, future translators will not all be built in theorem provers. Some might just be coded directly, but we would at least have a core reference implementation that you could look at to see, to help debug future ones, right? Future translators to see if they get the same equivalent results. So this is what we're creating, and then we will release this for everyone to modify, optimize our proofs, optimize the resulting C code translator, right? And work off of this. And then, of course, add way more translations than we will have in our initial stab at this. This is to demonstrate the feasibility of doing model checking in this way and provide a basis that the rest of the model checking research community can build off of. So in summary, the time has come for model checking community standards, and in particular, right, I'm focusing on symbolic model checking here. And what I hope that this keynote talk inspires you to do is first and foremost to participate. So on our website, which I will highlight after this slide, modelchecker.temporallogic.org. That's the website right here on the bottom of the page. If you go there, you have the opportunity to vote on a name for the intermediate language. It's kind of boring to just call it the intermediate language. So you can also submit your own suggestions for a name in addition to voting for ones other people in the community have suggested. We would like to come up with a name that everyone likes. And then you can also, for example, join our email list. You can be notified whenever we have a community forum for feedback, whenever we post new revisions to the design. You can also send us design feedback. So we have contact information. We welcome your feedback. We welcome your discussions. We welcome people coming into core design meetings, into meetings where we are looking at questions of, all right, what should we do for this part of the design or the translation? Do we need to change this? Is this representing what we want? So we will notify you of those. Please participate in our community forums. We have received so much amazing feedback from the community, and it has really changed and shaped the language that the draft that I've highlighted for you in this talk. So also look out for, coming soon, our PVS2C based translator chain from SMV++ through the intermediate language and down through BTOR2 and back. So we will be releasing that, of course, as soon as we have that finished for people to examine, build on, use as a foundation. So please look for that. And then also look to build on that, contribute your own translations, right? Contribute a translator between your favorite modeling language and the intermediate language. Tie in all of the models that you have been working with, that you have been verifying. Also, tie in your backend model checking algorithm, right? Contribute a translator from your tool, your backend, into the intermediate language. Help us build up this whole community standard and hook in all of those amazing tools that I highlighted in the hardware model checking competition. Hopefully in the future, right, the HWMCC, all of the tools will be using this intermediate language, and we'll be able to compare them, build off of them, combine them, and do phenomenal things as a coalition in ways that we never have been able to before in model checking. So please optimize all of this, expand it, compare research, please contribute. And I will happily take more questions, as well as I'm happy to show you the website here. So thank you very much for your attention. And yes, please let me know if there are questions.
Thank you for the very motivating talk. No questions came in the chat, but I see people are preparing to ask questions. So feel free.
Can I ask a question?
Sure.
Hello, thank you for the very inspiring talk. It's really wonderful, and Congratulations for this great effort. It's a amazing amount of work. I'm really impressed. I have a question concerning the soundness of this translation, because then I have a follow-up question if we want to contribute to that. Concerning the soundness of these translations, do you have the same semantic framework for SMV, for the intermediate language, and then for BTOR? Do you have the same semantic framework that facilitates this proof of soundness? How does it work?
All right. If I understand your question correctly, that goes back to this diagram. So we are still figuring this out. This is our plan, not a diagram of what we have completed. But the idea is, right, is that we would have a standard for the SMV language, and there have been a few over the years, right? So like Cadence SMV's input language was in very minor ways, but if you really used it, it was different from new SMVs. And then of course, new XMV has tweaked it slightly. We are tweaking it slightly, right? So yeah, so we need to have a very precise definition of what is SMV++, and what are we showing equivalence to? They said the intermediate language, we are actively revising as we do this. So we're trying to make the best version, but as we figure out that things are, for example, if we did something we didn't intend or had unintended consequences when we go to use it, then we re-examine, was that really the best way that we could possibly define that, right? And then we're using, for example, down here at the back end, BTOR tool 2 as output from BlueLector. And the idea of soundness would be carried by PVS, which is why Shankar actually made a very passionate argument and convinced everyone else that we should be encoding this in PVS specifically because we would have a rigorous proof to back up soundness, that the core languages as we have defined them in PVS really are equivalent. And so the translation, which is the proof in PVS, would provide soundness. Does that answer your question?
Yes, yes. So if we want to contribute and add a new language, then we have to provide a translator to IL. And then would it be required that all these are encoded in PVS or not? It's only for this core language that you provide, but if you want to contribute, it could be a less formal, say, approach to this translation. Or is it required that we really do the encoding PVS as well and then establish the soundness of this translation and so on? How does it?
Yeah, thank you. That's an excellent question. No, we're not expecting anyone else to use PVS. If you want to use PVS, you're welcome. You're welcome to do whatever you want to do. You're welcome to use a different theorem prover. You're welcome to not use a theorem prover at all and just write a translator and debug it in your own chosen way. Right? We just knew that the initial translation would get a lot of scrutiny from the community. And also, of course, right, you need to provide a basis for people to build on, optimize, compare to, right? You need a reference implementation. So it's particularly important for the reference implementation to have something like a PVS-based proof under it that we can distribute openly, that people can pick apart, can examine, can build off of. But yeah, you really hit the nail on the head with, if you want to add a modeling language, all you have to do is provide a translator to the intermediate language. That's it. And any way you want to implement the translator is up to you and should work, right? So all you have to do is get your modeling language into the intermediate language, and suddenly you can use all of the backends that have been created from model checking, and you can tie into the whole community.
All right, that's great. Final question. So the translation would involve two parts, like translate the language itself into IL and then translate the witness back to this to a trace in this language, or isn't it required?
Yeah, so we really have 4 translations going on here, right? So there are 4 large PVS libraries. So one is the translation from the representation, the high level modeling language, right, into the intermediate language that we have to prove correct. We have a second one from the intermediate language down to a representation that we can reason about with the backend engine. And in this case, we're using VTOR2, but yeah, whatever backend low-level implementation your model checking algorithm uses would go there. And then we have divided it in this case separately into also looking at a translation from the output of model checking, right, where you would get a counterexample, you would get maybe a proof certificate. Those are having different formats as people decide what the format should be, right? There's no standard for model checking proof certificates yet. That might be something that we have as a community in the future. So how do we take a witness, something that comes out of a model checking backend in one of those formats, and how do we make sure that we translate that back through the intermediate language and to the high-level modeling language in a way that preserves the states and the variable names and the information that makes the high-level model make sense, right? Because you can imagine that once you're hooking up every back end of model checking, that because of the different ways of reasoning about the systems, right, the different ways of optimizing the algorithms, the representations under the hood there, we have to be very careful to make sure that we got the states from the state transition model, right, at the high level language, that when we give a counterexample, it's in terms of those states, that when we return information about variables, it's the variable names from the high level model, right? So, so in some ways, this is less involved, right? Here we're translating the whole model down and doing model checking and then getting results. But here we also wanted to separately highlight that we need to make sure that we can pass the information up that makes the witness make sense at this level, right?
Okay, thank you very much.
Yeah.
Thank you for the presentation. It's a very challenging project, very interesting too. So to add a new method here, how do I know if I did it correctly? I will have the possibility to compare with the PVS.
Sure, that's certainly one way that you could do it, right? And that's one of the reasons why we were motivated to create the first translation in this way. So certainly once we have a provably correct translator, then one way that you could choose to verify and validate your own translator is to compare results with a PVS version, right? That we've created and supplied. Of course, there are many other ways, right? You could independently create your own provably correct one using a different theorem prover, using a different method, right, of your choice. But certainly we will want to provide the option that you could also compare with the one that we have put out.
And do you intend to make available some cases, big examples to really do the comparison between methods?
Yes, right. So we are going to put out a lot of examples. We already have a few hand translated examples just from fleshing out the intermediate language that are on our GitHub organization. So those are available right here in the language description on that page. We have a few different examples of what that would look like. And certainly as we go through and complete the work of finishing the translators, then we plan to generate many more. And then of course, having all of this available open source that you can interact with, the PVS2C tool is freely available. So you can also run that on our PVS proofs, generate this from scratch yourself, right? This entire tool chain that we are releasing as an initial stab at this is going to be completely free and open source and available on GitHub for anyone to take any part of.
Okay, so there was a question in the chat from Sydney, which has a quite long introduction about acknowledging the excellent talk and also the importance of the field. The question itself is whether you think this open source framework will help the popularization of model checking in general in the industry, because Sydney notes that these techniques, formal methods in general, are not very well known or popular or easy to use.
Yes, and that is thank you for that question. That is one of the major drivers of this work, right? Is that we have these forays, we have these glimpses into what can be, right? If we have a model checker, like in the case that I highlighted of new XMV, where we had a great model checker that was very well suited to the particular verification problem. We had a phenomenal verification problem where NASA needed to be able to prove in a way that was consistent with their formulation of safety cases for eventual flight certification. They needed a certain structure of proof, right? This was a very wonderful match in terms of a verification engine and a real problem. And like I said, it changed that system. And we have many examples of this, right? We have examples of railway and transportation and public metro systems, and as well as aircraft, spacecraft, satellites, all sorts of different things, right? And self-driving cars, where there are individual instances where model checking has made a phenomenal impact. And of course, we recognize that it's not everywhere yet. There are standards, and highlighting aerospace again, for example, the American Federal Aviation Administration, FAA, has created documents, and one is called DO333. And this document, I wouldn't necessarily say advocates, but it names formal methods as an acceptable way to achieve flight certification, right? And so we have this starting to be woven into official standards for developing these kinds of industrial systems. But as I highlighted at the beginning part of the talk, we have this stagnation where we're sort of shooting ourselves in the foot that we don't have the unification that we need to be able to really propel model checking research at the speed we want to go, to be able to keep up with these ever more complex autonomous systems, right? There is no reason why, if you're going to create a new back-end variation of IC3 and you are not a tool developer and you can't add it onto your own tool, but you're just a person with a really great research idea that could be a breakthrough, that could really advance things, there's no reason why you should have to implement an entire model checker and an expressive front-end language so you can interact with industrial systems just to show that your back-end algorithm really is an improvement, right? So yes, the idea is that we will make things easier for the research community to be able to unify all of the great research that's coming in modeling languages, in reasoning over real systems efficiently, in encapsulating and abstracting the important information from those systems in a way that allows us to verify it, and also all of the separate but wonderful research going on in terms of backends that are more scalable, that are faster, that have better performance. And then we are really able to propel model checking and forward in a way that allows us to demonstrate to the industrial community that this technique should be more widely used, right? And especially considering that those are quite separate focuses of research, the focus on both making rigorous modeling more accessible to industrial use cases is very important, but quite separate from the research in how do we make low-level model checking search algorithms scale more? How do we make them be able to reason over the different complexities that we're seeing in these types of systems, right? So if we can unify that, that gives us a huge advantage in terms of having this more widely adopted and bringing it to more systems. So yes, that was a massive motivator for this project. And thank you for asking about that.
Indeed, that was a really good question. Anybody else maybe with questions?
I'd like to ask another thing.
Okay.
It's not related to the presentation, but relates to your course, Applied Formal Methods.
Yes.
I really like this approach, this practical approach. I'd like to hear about your experience, if it's possible.
Sure. Yes. Thank you. That's another excellent question. So yes, I teach a course. I actually teach it in the aerospace engineering department, but of course it's cross-listed in computer science, computer engineering, and cybersecurity at Iowa State University. It's called Applied Formal Methods. It has a website that's quite easy to find with everything for the course posted on there if you're interested in precise details. But essentially, the idea of this course is that it teaches formal methods from a practical point of view. So there's a reason why it is taught in the aerospace engineering department. It is for people who are planning on building safety critical systems, on designing safety critical systems, maybe someone who's not even going to go to grad school. You know, you could take it as a senior undergrad to learn what are the formal methods, how do they work, what do they give me? What do they not give me? And how do I understand the results, right? To really understand what is the place and not just what is the state of the art now, but how you figure out what the current tools and capabilities are when a project comes up, right? So I walk through in the class many times the scenario of you are building such and such aircraft system, right? And your supervisor comes and says, okay, I need you to design this and you need to be able to certify it in this way, right? And then, okay, what do you do, right? How do you know are formal methods applicable at all? If so, which ones? Then which tools are applicable? What can I use them to say about this system? And what do I need to find different way to reason about, or do I need to signify as I can't certify this in this way, right? So the first half of the course is a survey of the formal methods, and we review things like the spin model checker and the new XMV model checker. We review temporal logic, specification, importantly, specification debugging and validation. So how to techniques and tools for making sure that you can make a case to other people that a formalism, a temporal logic formula, a model, etc., really represents the system that you're trying to verify. And we do units on theorem proving. So we've highlighted PBS in the course, we've highlighted Isabel in the course, had projects in those. And so the students try their hands at many different formal methods and many cases of verifying realistic examples in the first half of the course. And then the second half of the course is there's only 2 assignments. So one is that their homework / final exam is to formally verify a system. So I have a proposal for. Sorry, what?
Sydney, please mute yourself.
I'm sorry, I didn't understand what you're saying.
I think it was just an accidental unmute, so you can continue with the answer.
Okay. So anyway, in the second half of the course, they write me a proposal. I want to apply this formal method to this system. And then they do that throughout the second half of the course. And then in the class periods, we have presentations of research papers. So each student chooses a current research paper and formal methods, usually relating to their project. So using that skill that they developed in the first half of the class of how do you look at a problem, and then look at what is in the literature, what is online right now, and say, what are the formal methods and how do they apply to my problem? So they each practice doing that, and then they present a paper, analyze that paper in those terms. And then present their projects at the end of the semester. We have recently had several of the projects get published as case study papers. So I think we had 3 papers at the NASA Formal Methods Symposium last year that were all class projects for that class, where various students had decided to verify real aerospace systems, and then they had created quite interesting case studies. And actually in those 3 cases, none of them were going on to be researchers in formal methods. They were all just using them to verify some real system that they were working on for another purpose. But I really consider that a success. That was the point of having the applied formal methods course, is that this is teaching engineers to use formal methods and consider them as first-class citizens in the verification and design world.
Okay, if nobody else raises a hand or maybe writes in the chat, then I will not moderate myself more and ask my questions. I was really happy to chair this session, but also a little bit sad because I have to, let other people ask before I can. So I have a lot of questions actually, and probably we should continue this offline sometime. So the reason I'm super excited is because we are also developing model checkers, my research group actually, and we also had similar projects for software model checking and for systems engineering, basically. So intermediate languages, this is the good old problem of having n times m mappings, and instead of that, it would be nice to have only m plus n, right? So I would encourage you, by the way, to join us tomorrow if you can, because Dirk Beyer will speak about something similar in the software model checking community. So this is clearly a trend. And as somebody who did something remotely similar, I still painfully remember the critics and the skepticism that I've got. So I would like to ask you about how you defend yourself from comments like how this is not going to be yet another modeling language, right? This is something that we often get.
Yeah, and the idea, right, is that it's definitely not a modeling language. In fact, the community benefits from having a lot of modeling languages, but we would be well to standardize on just one intermediate one. I'm not sure why my slides are skipping around here, but hopefully I can get them to land on, there we go, on the intermediate language. Yeah, so we don't have something that occupies this space at all right now, right? It's a giant void. We have some great modeling languages. We hope there are more modeling languages, right? What's bad about yet another modeling language if it helps bring model checking to real industrial settings, if it helps specialize being able to transparently model in a way that you can validate easily some industrial system that we need to model check. That's wonderful. And we hope people create more of those languages. We're not doing that right now, but that would be great, right? And then of course, all of these things have intermediate representations of some sort for some definition of intermediate, but it's more like a very low level specific to that algorithm representation, right? That doesn't necessarily translate to another algorithm because these are of course very highly optimized. So we have nothing in this space, right? So it can't be yet another intermediate language if we really don't have anything here. And like I said, we studied extensively when trying to design what should be here all of the most closely related work, right? So when you have a successful tool chain in terms of model checking verification from a tool that takes something in a nice modeling language that humans would interact with and has been very successful at tying that to efficient backend algorithms, right? What does it do in between? So those were the things that I mentioned in terms of looking at SMTlib, VMTlib, various versions of that, Sally, Cryptol, what have various different developers of model checking tools done in that translation step and why, and what worked out, what didn't work out, what do they need to keep, what would they rather change, right? So we definitely looked at all of that, but none of those things that are in related work are really equivalent to what we were trying to do, right? None of them have the goals for our language where it's possible for any number of different high-level modeling languages or any number of different backends to really be able to represent in that language, right? They're all too limited in some way. They're all very specialized, understandably, to very narrow tool chain flow that they were designed to accommodate. And so we really need something that is different from any of the other things that have been created, and something that was purposefully designed for this space, right? I highlighted in bits and places throughout the talk how, as we have built future things, right, we have compiled them back to previous optimizations, starting all the way from the beginning with the first LTL symbolic model checkers, using some CTL representations under the hood, because that's what had been optimized in the intermediate representation of the tool chain at the time, right? Now, that, of course, as we build LTL, becomes not so efficient, and we want to design for LCL if we're doing LTL right, and not have this out of the way thing. And there are many instances of how this has evolved over time, right? So we have engines created for BDDs, and now we're adding, IC3 onto them later, right? So we have a need to change that. But there's nothing in this space. So that's how I would defend that, is that we're not creating yet another language. It's not a modeling language. It's not something humans interact with. It's meant to be parsable by machines. It's meant to be sufficiently expressive to fill the space we have pictured here, but not add to, for example, slow down tools, right? Be able to be optimized and parsed and translated through very easily. So we don't have that. We need that. And that's where we can all come together as a community and create something that we can agree upon here.
Mm-hmm. I really like the comparison to SMT-lib. I believe that we need something like that in model checking, and I'm really happy to see the constructs for formalizing the task, for formalizing or representing the return values and so on, the traces. So I also believe that this is something that we miss. We are running out of time, but I still have one question. And since I'm the session chair, I will give myself 2 more minutes for this. One of my concerns with this, which is also coming from experience, is that if we have a very low level and generic language, either the models will become very large, or we will lose high level information that could have been used to optimize model checking. Do you have any solutions for this?
Certainly that's an important trade-off, right? And that is what we have been looking at as we have been continuously refining our draft intermediate language, right? That we want to, we have to make it sufficiently expressive that we would not lose information. And that is why we have been, for example, looking at what information are people now starting to pass, looking at passing in the future back up from a model checker in terms of certificates, right? We want this to be extensible to, if in the future we have some sort of universal standard that every model checker has, for example, a certificate with these elements, then how do we make sure that we have an intermediate language that is sufficiently expressive that we would not lose any of that information, right? Because that's very important to retain and to be able to build that in the future, since we don't have a standard for that now. So that's a very important question. And then, like you said, we also don't want to impact the performance of model checking, right? So we want to provide something that streamlines model checking. We want to have the SMT-lib or the LLVM or the, name the successful intermediate language from another domain of your choice, right? We want to have that, right? Where actually at some point the intermediate language has been optimized to the point where there isn't a more efficient way that goes around it, right? Where going through this is actually the best way. And so all of the tools and techniques have started being designed to go through this path, right? So that's where each design decision we make, we are carefully weighing exactly the trade-off that you just named, right? Of, okay, do we have a way to capture all of the information? And now can we reduce, optimize, streamline, simplify the language so that we have the minimum computational impact while preserving that information. And so we have been having weekly meetings for a couple of years now. Our weekly meetings are often going over an hour. We have had, like I said, several other meetings with the technical advisory board, with community forums, and we have looked at each of these things, right? So in depth at the core bits of information that you need in this streamline, in this flow of model checking, and how we can represent that, but walk that line, right, of making as close to the optimal choice for that trade-off as we can at this point.
Okay, thanks. I personally, I believe that the fact that you have community meetings and that people are discussing these things are at least as valuable as any intermediate language. So thank you for speaking about this. I really hope that people here and people later who will watch the recording maybe will get inspiration to join this initiative. And thanks again for the great talk. We will continue the conference in slightly less than 1.5 hours with a tutorial, and now lunch break for Brazil, and some time to walk around for anybody else. Thank you again.
Thank you so
See you
much.
in the next session.